Once again, welcome to our channel Learning for Knowledge, and today we will continue our videos in the field of reverse osmosis, which relates with the water treatment. In this video we will discuss the different type of membrane material, their advantages and disadvantages. So after learning or understanding the basic term related with reverse osmosis, now we are moving forward and we are coming to the materials, types and other things. I hope you will enjoy this lesson, and if you still not subscribe our channel, please subscribe it. Reverse osmosis system, basically the heart of the RO base separation is semi-permeable membrane, and the membrane basically is the material, refers to the substance from which the membrane itself is made. Membranes may be porous or non-porous, and there are different type of materials which are used in the preparation of membrane. Like membrane material may be polymer, metal, liquid, zeolites or composite materials. The material properties of the membranes may significantly impact the design and operation of the wastewater, and the performance of RO membrane is generally determined by mainly two parameters. First is water flux and second is the salt rejection. So material of the membrane plays an important role in the performance of the RO membrane. Basically there are different type of membrane materials are available in the market, and continuous development is going on in the preparation or synthesization of the membrane material. But now generally at this stage the two type of famous materials are historically available in the market. First is cellulose acetate based material, which is abbreviated as CA material, and second is polyamide based thin film composite membrane. These composite membranes are relatively latest, and initially a polyamide based membrane material was started in 1970s. So cellulose acetate based RO membrane, historically if we look in the history, the first RO membrane plant was operated with hollow fiber cellulose acetate based material. Cellulose acetate membrane has following advantages. Before looking into advantages, you see this is the basic structure of cellulose acetate. It is polymerized and this long chain polymer, and this is the basis. There are different type of cellulose acetate, which are diacetate and triacetate type of polymeric material or membranes are available, and their amalgam or composites are also available. In short, if we look in the advantages, the relatively smooth surface morphology of the membrane offers better protection from fouling. Because the surface is more smooth, so there is a less chance that the material coming from the pre-treatment section, if left over, it will not deposit in the pores or uneven surfaces of the membrane. Second is higher chlorine resistance, being able to tolerate up to 1 ppm. This is a big advantage, because there is due to biological growth, sometime we have to kill these biological compounds or material. We need a continuous dosing of chlorine or some oxidizing agent. These type of membrane, which is cellulose acetate, are more resistant to the membrane. So these higher chlorine resistance, being able to tolerate up to 1 ppm free chlorine. So if by mistake or in a process we add more free chlorine, then it will tolerate much better as compared to polyamide type of membrane. So this is a big advantage. Then third one is high rejection rate and high durability is unique and irreplaceable especially in seawater desalination industry, because in seawater the higher TDS as compared to brackish water, so this membrane offer a high rejection rate and high durability. So these are some basic advantage of cellulose acetate. Beside these advantages, there are some disadvantages of this type of membranes. First is low mechanical resistance. Second, hydrolysis in acidic. This type of membrane hydrolyzes in acidic and alkaline environment. Therefore, a very narrow operating range, pH range, is available. It can smoothly operate in 4 to 6 pH range. If pH goes down, like in the below 4 or higher than 6, its life becomes short and it hydrolyzes, and this is a big disadvantage. So operating pressure, third one is operating pressure of cellulose acetate membrane ranges from about 200 to 400 psi. So pressure above this value, like 2.8 megapascal, will result in compaction of the membrane. Due to this compaction, when much pressure or high pressure is applied, membrane will essentially crushes the membrane and making it even denser. When membrane become denser, more pressure is required to get the same quantity of the product water. And another important disadvantage is rejection of silica, and it has 80 to 85% rejection capacity of silica. So nowadays in good industrial plants where boilers are operating at high temperature and pressure, we need a purified water, and presence of silica may not be a good thing. So that's why this disadvantage make them less use of these type of membranes. Due to these disadvantages, DuPont de Nemours, a company, developed a polyamide based hollow fiber material in 1970s. So if we summarize all of these characteristics of cellulose acetate RO membrane, so membrane type homogeneous, asymmetric, salt rejection 95%, silica rejection around 85, pH range of the water 4 to 6, feed pressure with brackish membrane 200 to 400 psi, temperature tolerance up to 35 degree, and surface charge neutral. This is a good thing. Chlorine tolerance up to 1 ppm, good. Biological growth, metabolized membrane. So fouling tolerance good, and surface roughness smooth. So these are some advantages and some disadvantages of this membrane, and these are summarized in this table. The second important type is polyamide and its composite membranes. So polyamide membranes were developed in an effort to improve upon the performance of CA membranes, cellulose acetate membranes. In particular, the higher operating pressure and relatively low salt rejection of CA membranes were holding back RO technology from becoming more commercially acceptable in 1960s to 70s. After the invention of these polyamide type membranes, RO plants are becoming more commercial and more popular in the world, and their application is now growing so very fastly. This is the basic structure of aromatic polyamide membrane, and we will not go into the detailed chemistry of these. We are just looking at the basics of this material. So there are some limitations of polyamide membrane composite. First, with this, due to rough surface, this is not so much smooth as compared to CA. So surface morphology of polyamide membrane, foulants can be captured and held by the membrane. So this is you can say that there is some fouling tendency in this type of membrane. The charge on the polyamide membrane is negative due to nitrogen, which has a lone pair, so thereby attracting cationic polymer coming from pre-treatment equipment. If some of the cationic polymer comes from the from this pre-treatment section, if we have a cation or anion exchange resin available, or some of the membrane ultra UF membranes, and it will leach out from those membranes, then the charge on the poly membrane negative, so it will attract, and now the efficiency of this membrane become reduced. Polyamide membranes cannot tolerate free chlorine. Big point, very big limitation, or any other oxidizer. This means after 200 to 1000 hour of exposure to 1 ppm free chlorine, the membrane rejection will have approximately double the salt passage. So chlorine attack is faster at alkaline pH than at neutral or acidic. When this membrane oxidizes, the passage for passing, or the pores of the membrane expand and more salt pass in the permeate. Now we come to the advantages of polyamide based membranes. Polyamide membranes can tolerate higher operating temperature as compared to CA, and maximum temperature allowable is a function of pH. It depends on the pH of the water. So polyamide membranes have much broader pH range, operating range or operational range from 2 to 11. So operating pressure for polyamide membrane is generally lower, ranging from about 150 to 400 psig. This is because the polyamide membrane has a thinner rejecting layer offering minimal resistance to permeate flow. Basically the operating pressure is now reduced. Advantage, this is the advantage, and more product is formed. Why this has happened? Because the polyamide membrane has a thinner rejecting layer. The main layer is very thin, so by applying less pressure it allows more product to be formed. Next is the passage of salts and silica is much lower for polyamide membrane. This membrane does not allow more passage of silica and salts. Some membrane can achieve even 99.7 plus minus % of rejection on standard test solution. What is the standard test solution? The standard test solution is 2000 ppm of sodium chloride solution at 225 psi, 1.6 megapascal pressure, and at a temperature of 25 degrees centigrade, and its pH is 8 and recovery is 15%. The salt passage at this rejection is only 0.3%, while the salt passage for high rejection CA membrane at 98% rejection is 2%. So it is approximately 7 times more. So the salt passage is nearly 7-fold lower for polyamide membranes than for a CA membrane. These are due to these advantages, especially the pH range. Importantly, pH range and low pressure make it more suitable as compared to cellulose acetate. However, both type of membrane are in use nowadays as well. Some of the various properties of PA membrane are summarized here. So homogeneous, asymmetric, thin film composite, this is one of the type. Salt rejection 98%, silica rejection 96%, pH range 2 to 12 or 11, feed pressure in brackish membrane 145 to 400 psi, and temperature tolerance up to 45 degrees C, surface charge negative anionic, chlorine tolerance less than 0.2, and biological growth causes membrane falling. This is again not a good thing for membrane operation. Following tolerance fair and surface reaction. If now by putting these properties or comparing these properties with the CA membrane, now we have to use or decide what we want to do during the water purification. That's why both membranes are using. And there is a comparison. So if we compare thin film PA membrane and then CA membrane, so salt rejection now it's 99.5% and it is around 95%. Still the more research work is going on now, it is increased up to 98%. Net driving pressure lower due to thin layer, and here is the higher. Surface charge more negative, less negative. Chlorine tolerance poor, fair, and cleaning frequency higher, here lower. Organic removal higher, here lower, and biofouling more susceptible, this is less susceptible due to its nature of CA. Biodegradation none, here higher, and pH tolerance 2 to 13 or somewhere 2 to 11. Best operation is 2 to 11, and it is limited between 4 to 8, but best operation in 4 to 6 range. Besides these, other membrane materials are available. For example, Polyether is another type of thin film membrane. This membrane differs from polyamide membrane in the surface charge and morphology. Polyether membrane has a slightly positive charge to them. Further, the surface of PU membrane is smooth, similar to CA membrane, thereby minimizing the potential for fouling. Hydronatic CPA membrane is an example of polyamide polyurea blend composite membrane, but they are not so much famous nowadays as compared to polyamide, but still some companies are manufacturing and are in use. Now there are one of the, you can say, case study with the passage of time. Here we are comparing the cellulose acetate and polyurea composite base and polyamide based membranes and their development with the passage of time. This comparison is made up of 3 generations of brackish water RO membrane at Englewood Water District. Now these are some parameter: design parameter, maximum feed design, normalized flux and relative membrane. Now train A, which is in 1982, is operating on cellulose acetate blend type membrane. Its design feed water TDS 4700 and maximum design feed pressure 600 and normalized flux 0.041 and energy used is 100. Relative energy usage for initial, if it is 100, then remaining will be in the percentage of 100. Now the same train A in 1986 composites polyurea type membrane is used, and this membrane has been replaced with polyurea composite. Now its design feed water capacity is design feed water TDS 6000 increased, maximum design feed pressure 420, so it can operate at less pressure, and max normalized flux per psi 0.057, so more water is you can say get as compared to this one, and the energy consumption is 72. So if we use 100 kilowatt hour, then it is 72 or 100%, and this is 72% of this. So in train B and C in 1986 composite polyurea 6000 and same thing, and now this is further increased in 0.069 and 59 relative pressure. In 1989 trains D and E composite fully aromatic polyamide membrane. Now although TDS has been increased, but maximum feed design is reduced at 335 psi stage 1 and normalized flux is increased 0.082 and the relative membrane energy use is 50. So you can say with the past within a decade, these material are going to be advanced, membrane material are going to be advanced, and due to this advancement more TDS water can be treated at low energy. So operational cost of this RO with these type of membrane has been reduced. There is another comparison, 4 type of membrane. Now this is only for sake of comparison and based on the different type of materials. So performance comparison of thin film nanoparticle membrane. This is one of the most advanced membrane material. Quantum flux with conventional thin film composite membrane. These 4 companies are making these type of membrane, which have the model number Nano H2O, Hydronautics, Dow Filmtech and Toray Japan. These companies are from USA, this is from Japan. So membrane area, if we have same values in feet square and meter square, permeate, production rate 9000, and here with the same area this membrane produce less product water, permeate, stabilized rejection percent for this nano membrane 99.85, here 99.8, 99.8. So similarly stabilized boron rejection 93, 92, 91, here 95, and feed spacer thickness in mils 28 due to less size, 34, 28, 28. Now with reference to this, or what is the advantage of this nano H2O, which is latest material membrane? Here the 25% lower salt passage. This due to nano technology, the salt passage is becoming more smaller and smaller. So the size passage, if we compare this nano H2O with hydronautics, then the size passage of nano H2O is 25% lower salt passage. This is the advantage. Similarly in Dow film tech, and as compared to Torre, 25% lower salt passage and 6% higher productivity, because here 8500 meter cube per day production, here 9000. So due to these advancement and availability of nanotechnology based membrane, the efficiency of the membrane or RO plant become increased. So these are the some you can say advantages and disadvantages of the material, mostly used material, which is polyamide and cellulose acetate. But here we also showed some of the advantages of nano particle based membrane material. But still there is a lot of research and development is going on. Because the RO is basically based on the membrane material, and its efficiency is mostly dependent on the membrane material. So we have to be very careful when we will select the type of membrane material. So we will continue our videos on this reverse osmosis and then water treatment aspects of the water. Wait for our next video, and if you still not subscribe our channel, please subscribe it.